Physics fun with Mr. Bywater. Hey guys, we're going to do some more physics, some kinematics, two-dimensional kinematics to be exact. We're going to do a little bit more than what we did in the last one. The last one we basically started horizontally, so we didn't have any vertical initial velocity, so this is going to be a little bit different. Okay, I left this up here because I wanted to see all the fun we had last time. So here's the fun we're going to have this time. Ta-da! All right, so here we go. I have a cannon that can shoot an object with an initial speed of 20 meters per second. If I shoot it at an angle of 30 degrees, where will it land? Okay, so again, we're going to assume flat ground. We're going to assume no friction, air friction, all that stuff. We're going to make those basic assumptions. From here, we're ready to go. Okay, now this is a little different from the last one because it's being shot at an initial angle, right? It's not starting horizontally. So you can tell, again, this is a projectile. It's something flying through the air. That's why we're going to go to our SUVAT equations in our two-dimensional kinematics. So here we go. We've got our horizontal and our vertical. And then we've got SUVAT, so S-U-V-A-T. All right, now really it would be nice if I draw a picture, kind of get an idea of what's going on before we get started because I love drawing. Actually, no, it's whatever. I'm just a visual person. So we've got our ground, we've got our cannon, which looks something like this. Yes, that's an amazing cannon. And then the object is going to fire and land. It has an initial velocity right here of 20 meters per second. It also has an angle. The initial angle is 30 degrees, and that's all that's given. Okay, and the question is, when is it going to hit the ground over here? Now, obviously, this is one of a million types of questions like this that could be asked. They could ask, what's the maximum height? At what angle will it hit the ground? At what speed will it hit the ground? All of these varies. Actually, what speed? That's easy because we know that if it goes up and comes down, if it's at the same level as before, it's going to have exactly the same speed that it started with. So speed is easy, 20 meters per second. But those other questions would require a different use of kinematics, but still using the same format. Okay? So remember, this is just an example. It's trying to get you through one, but you're going to have to figure out how to apply this to the other situations. But they're all basically the same thing. Okay, so here we go. We got horizontal. So it's asking for our horizontal displacement. So from here to there, what is my horizontal displacement? And the question, well, that's what it's asking for. That's what I want right there. So S. Okay, now I've got the initial horizontal velocity. This X is only horizontal information. Don't put anything vertical there. So my initial horizontal velocity, well, I'm going to have to use my vectors, right? Because it's being launched at 20 meters a second. So what I'm going to do is I'm going to step over here to the side and I'm going to say, okay, my object has an initial velocity of 20 meters per second at an angle of 30 degrees. So if it's that angle, then how is that built up of the horizontal and vertical pieces? What is the horizontal velocity there? And what is the vertical velocity there? Because I'm going to need that on the other side of my little table here in just a little bit. So I'm going to figure out those two components. So for the horizontal, that's the adjacent side. So I'm thinking SOHCAHTOA. And so I'm thinking adjacent over hypotenuse, that's got to be cosine. So I'm going to go cosine. Cosine of 30 is equal to the adjacent over the hypotenuse, which is 20. And so it's 20 cosine 30. All right, so I can go ahead and I can punch that into my fancy schmancy calculator here, which is the same as everybody else, except for the fact that somebody put my calculator onto degrees. How dare you? Okay, so hold on. I'm going to have to put this into radians real quick. Maybe I'll just take this segment out. So document settings. Need to go to radians, make it the default. Okay, yes. Okay, so now I'm ready for 20 sine 30. There we go. 20 sine 30. And it gave me a negative 19. Oh, because it's in radians. Oh, that was dumb. It should have been a degree, shouldn't it? Oh, at the power, yes, that was 30. All right, so now we got to go back 2 degrees. Now we're ready to do the 20 sine 30. And I get 10, which you probably could have gotten from your special triangles anyway, but I want to give you time to do it. So 10 meters per second. That's because I didn't do man. This is ridiculous. Okay, it's not sine, is it? It's 20 cosine. 20 cosine 30. So 20 cosine 30, which is going to give me 17.32. So I'm going to write that down. 17.32 meters per second is the horizontal. The vertical, of course, is going to be opposite over hypotenuse. So that's going to be sine of 30 equals opposite over 20. Or you could recognize this as your special triangle, 30, 60, 90. And because of that, this has to be half of that. Either way, you can get it 10 meters per second. So now I'm going to put all that information into my table here. I've got my initial horizontal velocity is 17.32 meters per second. My initial vertical velocity is 10 meters per second, and it is upwards. Okay, this one is to the right. Okay, at this point, I can now continue to put in information. Okay, the horizontal final velocity, recognize that as my object gets launched, as soon as it leaves that launcher, then the horizontal motion doesn't have any forces, because we already said there's no air friction, so therefore it continues to move at a constant horizontal velocity. That doesn't change because there's no horizontal forces, no horizontal acceleration. So therefore, that will be 17.32 meters per second. Acceleration, of course, is 0, and we don't know the time. We don't know how long it's going to take for it to land yet. Okay, let's look at the vertical information. Vertical information, vertical displacement. Now, this catches some people because the vertical displacement, I start here at ground level, and I end when it hits the ground. So what is the vertical displacement? The vertical displacement is 0. Yes, I know it doesn't end up where it started, but vertically it does. All it did, if you look at this beginning and ending point, is that it moved horizontally. That is the displacement. It had a horizontal displacement, no vertical. Okay? Move in. Final velocity, you may be able to figure out the final velocity. We had the discussion that if you start and end at the same height, your final velocity is the same, except now it's downwards. If you don't get that, that's okay. I'm going to show you that it's okay to not have that number. I'm going to leave it blank in case we don't think about it. But try to think about it, because any extra information you have is always going to be great. So you could put a negative 10 meters per second here to show that it's the same speed, it's just now it's going down. Okay? The acceleration, of course, is negative 9.81. I'm going to do negative 10 meters per second squared just to simplify my calculations on the board. I'll be able to do things a little bit quicker. And of course, again, I don't have the time. Okay? So, from here, again, I want the horizontal distance. Where will it land? This is what I want right here, this S. But you'll notice, similar to the last question, I have initial final velocity acceleration, which if I put into this, my acceleration being 0 will be multiplied by the displacement, and it will go away. I don't want my displacement to go away. I want to be able to find it. So at this point, I'm going to have to go with the y's first, just like in the other question. So I've got S, I've got U, and I've got A, and of course the link between the y and the x is the time. So I need to find that time there. So I need everything except for the v. Notice that this could be the same equation as last time. So S equals ut plus 1/2 at squared. So S, 0, equals U, which was 10, t, plus 1/2 times A, which is negative 10, times t squared. Okay, at this point, I should be able to solve that. Okay, so I got 0 equals 10t minus 5t squared. I can factor the 5, I can factor the t. Don't divide because you lose answers when you divide. So I'm going to go 0 equals, I'm going to go negative 5t because I like my t to be, actually it doesn't really matter because I'm factoring it out. So let's go ahead and leave it as 5t, why not? So that'll be 2 minus t. And so from that, you should be able to get your 2 times. You know that time could be 0, but time could also be 2. Now, of course, why is it giving us these 2 answers? It's because the equations are stupid. They can't think for themselves. You have to think. Oh no, I have to think with the bow. Yes, you have to think. You have to recognize that all you told it was that it has a displacement of 0, initial speed, and acceleration. Well, when is it going to have a displacement of 0 vertically? Well, at the beginning, it hasn't been displaced yet, and then at the end. And so your 2 answers there are at the beginning and at the end. You have to figure out which is which. Good luck. I'll give you 1 guess. 2 is what you want. You want time equals 2, so we're going to put into 2. So 2 seconds. That then carries over to the x. The time when it hits the ground is also the time that we want here. And so now, of course, you have all the information that you need in order to be able to find s. Once again, you can use any of your SUVAT equations, whichever one you want. However, my recommendation is this one because it seems the simplest to me. So I'm going to go s equals v, which is 17.32, plus u, which is 17.32, times t, which is 2 seconds, all over 2. And so my final answer is that s equals 14.64 meters. And there you go. It will land 14.64 meters from the place where it was launched. And again, all sorts of questions could be asked here. You're going to have to deal with those questions and how to apply those. But the principle here is the same. Put in your x's, put in your y's. Most of the time, if they give you a question like this, you can expect that you're going to work with one variable first, find the time, which will then carry over to the other variable. Okay? This vector stuff that we did here at the beginning, sometimes we have that initial velocity. Those are the easy ones because we can break it into those very quickly and very easily. Sometimes it's actually the opposite, and we're going to do one of these for homework tonight. I'm not going to make a video of it. I'm going to let you try it on your own. Sometimes we have to deal with it because if you don't know the initial velocity, maybe you're given the distance or something. So we actually have to work backwards. When we work backwards, we find the vertical velocity that we need. We find the horizontal velocity that we need, and we put them together to figure out what that initial velocity is. And so be prepared to work backwards, forwards, inside out, upside down, whatever way we decide to work. We've got to be able to work in all those directions. All right? That's it. Good luck.